Okay, Jai Hind everyone. Myself Achintya as assistant professor in Department of Information Technology at Ajay Kumar Garg Engineering College. Okay, now I will discuss some concept of normalization and functional dependency. Okay, especially how we will solve the questions of normalization based on the functional dependency theory. Okay, so before exploring normalization, we will see what is the normalization. Okay, so normalization is basically it is the concept or you can say technique by which we eliminate the redundancy. Okay, redundancy normalization is a way this is the technique by which we could eliminate the redundancy, means how the repeated data could be removed. Okay, could be eliminated up to the extent so that the redundancy will be minimum. So the objective is to minimize the redundancy. The objective is to minimize the repetition of data in a relation. Okay, so we will see. So normalization, it is a process to remove the repeated data, or you can say the redundant data, repeated data or redundant data. Of course, if a data is repeated, so what is the use to have multiple copy of same data? So that is the not the effective way. It will take storage and all. Okay, so the aim is to eliminate, or you can say reduce the redundancy, repetition of data from the relation or table. Okay, for example, say we have a relation student. Okay, and the attribute of these student are, say, student name, course, phone number, subject, teacher and marks. These all are the attribute: name, course, phone number, subject, teacher and marks. Suppose if we create this table, so here we see if we add so many attribute, our combined attribute from we can say many attributes, okay, in a single relation, we will see that there could have more repetition, more repeated data. For example, here we could see that if a student name is if a student having 6 subjects, okay, if a student are taught 6 subject, right, so phone number will be repeated. Every student will have same number and every student is teaching 6 subject, so 6 times phone number will be repeated. Okay, why 6 times phone number will be repeated? Because student is teaching 6 subject. So if a student is taught 6 subjects, so this will be repeated, phone number will be repeated, okay, and everything will be repeated in fact. Okay, so how we could minimize this? So better the relation must decompose. These subject and all should be in another relations. Okay, and of course, just to minimize, just to have less repetition of data, we should avoid combining attribute from so many relations, or we should avoid so many attribute in a single relations. Okay, so how we could do? Okay, how we could decompose a relation? That comes under normalization, and the purpose is to have less or reduce redundancy. Okay, so here we can say that the phone number is repeated for all the subject of a student, hence resulting into redundancy. So design of a relation schema should be such that it should avoid combining attributes from multiple entity types and relationship type into a single relation. So one technique or one key approach is to not have so many attributes in a single relations, because this could cause repetition of data. Okay, so normalization is nothing. Normalization, it is a process, it is a technique just to remove or reduce repetition of data, redundant data. Okay, so normalization based on so many theory are categorized into types of normalization. So the types of normalization are 1NF, first normal form, second normal form, third normal form, and BCNF, Boyce Codd normal form. So from BCNF to first normal form, they are based under the theory functional dependency. Fourth normal form based on the theory multi-value functional dependency theory, and fifth normal form is based on the joint dependency. So the normalization, I mean how we could remove, how we could reduce the redundant data, that could be achieved by knowing all this theory. So from BCNF to 1NF, it is based on the concept theory functional dependency. Fourth normal form is based on the multi-value dependency, and fifth normal form is based on the joint dependency. Here we will today I will explore basically the theory, I mean these kind of normal form, means first normal form to BCNF under the functional dependency. Okay, we will see what is the functional dependency and what are these normal form, how you can crack the questions, because every year GATE includes numerical question based on the BCNF, 3NF, 2NF and 1NF. Okay, so here we will explore these normalization, I mean from BCNF to 1NF. So like if we increasing in this order, so BCNF is the highest form of, BCNF is the most strongest form of normalization under the functional dependency. 3NF is comparatively less than BCNF, second NF is less than, I mean 3NF, and 1NF have many, I mean repetition data. So highest form of normalization or most strongest form of normalization means the repetition data, redundant data will have the less number. Okay, repetition will be quite less. As the stronger it becomes, repeated data will be reduced up to very much extent. Okay. Okay, so let's see what is functional dependency. So how you could define what is functional dependency. So suppose a relation R x y, say for example x and y is the attribute of that relation. You can say even assume x and y both are set of attributes even. Okay, not a single attribute, but it could have set of attribute, more than one attribute, you can consider it. Okay, so what is the definition, what is the functional dependency? So functional dependency, say for example if we have a relation R consists say set of attribute x and y. Okay, so functional dependency is denoted by x arrow y, means x this is said as x determine y, or we say y is functional dependent on x. So what is the meaning? Meaning is if x repeat, then y also repeat. Okay, so functional dependency, what functional dependency say, if x means if left hand side repeats, their right hand side also repeat, then we can say left hand side determine the right hand side. That is the point. Or we can say right hand side is functional dependent on the left hand side. And what is the left hand side and what is the right hand side? Left hand side and right hand side both are attribute, or you can say list of attributes. That's all. So mathematically, if we can write for any two tuples in a relation, if the value of first tuple is equal to T2x, means if T1x is equal to T2x, means the corresponding value over that attribute between two tuples are equal. So if the corresponding value of two tuples are equal, then in y it is also be equal. If it is so, then we can say that x determine y, or we can say that y is dependent on y is functional dependent on x. That's all. Okay, so functional dependency, this is a theory, and the theory say that if x repeat, then y also repeat. If it is so, then we can say that x determine y. Now this functional dependency have 6 inference rule. Inference means how you can infer from that. Okay, so one is reflexive rule. So reflexive rule say if y is, say you would have to consider like this. This is the left hand side, this is the right hand side. Okay, or you can say simply if y, you would have to consider x and y is a single attribute or a set of attribute. Okay. So if y is subset of x, okay, x and y are what? They are the attribute. So if y is subset of x, then we can say that x determine y. If y is subset of x, so we can say that x determine y. For example, if we have attribute a, b, c, d, so we can see the b is subset of a, b. So what we can say, a, b determine b, because b is subset of a, b. Okay, a, b. So a, b could determine b. If right hand side is subset of left hand side, then left hand side determine right hand side. Okay, so we can say like this. Here we say that b is subset of ab. Okay, so ab determine b. For example, we have student. Okay, so student roll number, name, branch, and all. So we can say that like roll number is subset of roll number comma name. So we can say the roll number comma name will determine the name. That's all. So this rule is called reflexive rule. What is the augmentation rule? Second inference is augmentation. If x determine y, then we can add some attribute which is common, which is the same. So augmentation rule, if x determine y, then we simply inference xz also determine yz. There is no point in that. For example, if a determine b, then we can say ac also determine bc. Yes, we could add same attribute right hand side. Transitive rule, say if x determine y, and y determine j, they belong x determine j. Means if x determine y determine z, then we can say x determine j. Transitive relation. So transitive rule is this. Union rule, say if x determine y and x determine z, then we can say it logically determine x determine yz. Okay, union is what? Left hand side must be equal. Left hand side determine say some right hand side another. So left hand side is equal. X determine y, x also determine z, then we can say x determine yz. Decomposition rule is just reverse of that. If x determine yz, then we could write, or we can say it functionally determine x determine y and x determine j. And the last one is pseudo transitive rule, just like a transitive rule. So if x determine y and yw, if it is not w, then it becomes the transitive. So pseudo is what? Y and something more. So yw determine z, then we could write xw also determine z. So the above 6 rules also called Armstrong axiom. Okay. So functional dependency. So what is functional dependency? Functional dependency say that if attribute value, if x repeats in a relation, if x and y are attribute, a set of attribute, and somehow the value of x repeats, and the value of y also repeat. If the value of x repeat, okay, then y also repeat, then we can say that x determine y. Okay, if x repeat, then y also repeat, then it is called y is dependent on x. And this functional dependency has 6 inference rule. One is first one is a reflexive, second is augmentation, third one is transitive rule, fourth one is union rule, fifth one is decomposition rule, and sixth one is a pseudo transitive rule. Okay. Next comes closure of it. How you can find closure attribute, because in numerical somehow you would have to find the closure just to find out, I mean, key of the relations, super key or candidate key. So what is closure? Closure, say if A and B are attribute. So closure attribute is, I mean, what are the attributes which is determined from that attributes. Okay. So given a set of attributes, say alpha, define the closure of alpha under given functional dependency f as the set of attributes that are functionally determined by alpha under f. Means under given fd's, what more alpha can be determined. Okay, like if we have fd a determine b, so a closure means what are the attribute which could be, I mean, inference from a. So a closure denoted by a plus, and they will be the all the, I mean, attribute which could be determined from A under the given FDs. Okay. So closure is the set of all attributes which is determined by the that attribute under some given functional dependency. For example, see in this question, if you want to find the candidate key, what is the approach to solve these type of questions? Here we have given list of attribute and some functional dependency, and we want to find the candidate key. How you could find? So the basic approach is to first find the closure of attribute, and by that closure, I mean if attribute could determine all the attribute of that relation, means that particular attribute becomes the closure of attribute. For example, here these all are the kind of FD given. So we will find AB closure, CD closure, and all that, and the combination of even that. So we have the attribute A, B, C, D, E. Okay, there are 5 attributes. So if an attribute or set of attribute determine all those 5 attributes, then that attribute become automatically the super key or key. Okay. So just to find out AB closure. Okay. So what will be the AB closure? So AB determines C. So the first rule is to write closure of any attribute. Like if you want to write AB closure is denoted by like this. Okay, AB. So first we have to write AB, and what AB determines C, and out of 6 inference rule, if this AB closure determines say any more attribute, then we can say that this is the closure. So is there any attribute that could be derived from AB? It is not so. Okay, because there is no AB closure ABC, and C is not determined. Okay, C does not determine anymore. Okay, similarly we would calculate CD closure. So CD closure will be CDE. Okay, and CDE already, and DE determine this, DE determine B. So you could write CDEB. So what is not that? A is not here. So if we determine ACD closure, so this ACD determine all 5 attribute A, B, C, D, E. So we can say ACD is candidate key, and like that we can determine. Okay. So to find out the candidate key or super key, we would have to calculate or find the closure of attribute, and if the closure of attribute determine all the attributes out of applying all inference rule based on the FD, then we can say that that particular attributes will be the candidate key or super key. Another set of questions comes to, can 2 set of functional dependency, if there is a say one set of functional dependency and there is another set of functional dependency, how we can say that both set of functional dependency are equivalent, or when it could be equivalent? Okay, so the basic rule, if we determine the closure of both functional dependency and they are equal, then we can say that both are equivalent. But this is the heavy approach. Heavy means it will take it is a lengthy process. So one way to prove how 2 set of functional dependency are equivalent is if we can determine, like suppose here F1 and F2, 2 set of functional dependency are given, or let's say in the example F and G. So if by using F we can determine G, or by using G we can determine F. Okay, by using F, if we could determine this particular FD, or by using G means these FD, we can determine all these FD, then we can say that they both are equivalent. Here we could determine, just you could apply reflexive, transitive, union, decomposition and all rule, we could determine here. Here is the process given here. Okay, so for example, like this one is the first set of FD. So out of that, if we could determine A determines CD. So let's see, A determines C, AC determine D. So AC determine D means CA determine also D. So you just apply what? Pseudo transitive. So it becomes AC and CA. So A determines D means A determine D, A determines C, A determine D. Just apply union rule, you could find out A determine CD. Similarly, E determine AH. How you can find E determine AH out of these? Here we see E determine AD. So out of that you could write E determine A, E determine D, decomposition. Okay. So E determine A, A determine D. Now E determine A, E determine H. So you just apply union rule. So it will become E determine AH. So from F we can simply determine G. Similarly, from G if we can find out all 4, 1, 2, 3, 4 FD, then we can say that both are equivalent. Okay. So this is the approach, this is the practical approach, this is the quite easy approach as comparison to find out closure of the attributes. Okay. So what we will do? By using one set of FD, if determine second set of FD, by using that second set of FD, if you determine first set of FD, then we can say both are equivalent, and here they both are equivalent, we could find out. Okay. So again come back to the normalization. So we have studied functional dependency and the inference rule of functional dependency. So the purpose is what is the purpose? Purpose is to normalize how you can find that given relation, and we'll have so many attribute given under given FD, then how you can find out that these these relation under the given FD will have what type of normalization, either will be in first NF or 2NF or 3NF or BCNF, how we can determine. So here we have a rule. Rule say BCNF, BCNF is the highest form of normalization under the FD. So BCNF is what? So let's see, relation R functional dependency set F will be in BCNF if every functional dependency alpha determine beta in F closure satisfied any of these two conditions. Every FD of given relation and FD, if they satisfy any of these two conditions, then we could say that it will have normalization. And what is the condition? Condition say either the FD is trivial functional dependency. Trivial means functional dependency means if right hand side is subset of left hand side of given FD. Okay. So we can say that it is trivial functional dependency. Okay. First one is reflexive rule. Okay. Or alpha should be the super key. So alpha is what? Alpha means left set. Okay. Left side. There will be have some set of given FD. So alpha will be all left. Okay. So if all left of given FD or what? Super key, then we can say it will be BCNF form. If any alpha, alpha means left hand side of all FD, if anyone is not key, then it will not be BCNF. Then we will go for given question will have BCNF or 3NF or 2NF. The basic approach is we would have to decide, we would have to find out the left side of FD. If we can prove the left hand side of FD as a key, then the question will be of BCNF normalization. Okay. They are in BCF normalize. Okay. If any FD of given set will not be the key of left side, means any FD and its left hand side is not key, then we will go for 3NF. And 3NF say right hand side. So right hand side be super key, means beta. If you can find it is the prime attribute, then it will become the 3NF. Let's see one by one. So again concept of prime attribute. Okay, because for 3NF we would have to know what are the prime attribute. So prime attribute are nothing but prime any attribute which are part of potential key, any key or super key or candidate key. If it is the part of that, like suppose ABC, okay, ABC is super key. Okay, so A is a prime attribute, ABC is a prime attribute, B is a prime attribute, BC is a prime attribute. Any combination of ABC is, we can say, prime attribute. The prime attribute is nothing but it is a part of any potential key. Okay. Okay. So if alpha, I mean left hand side of given FD is not super key, then we will go for the 3NF. And for 3NF, the condition is beta, means right hand side must be prime attribute. And what are the prime attribute? Part of potential key. And for 2NF, we would have to show that full functional dependency. So a functional dependency is XY is full functional dependency if removal of any attribute A from X, dependency does not hold anymore. Let's see, we have a question, then you this thing could be more explored. For example, we have a relation student performance and the attribute are name, course name, roll number and grade, 4 attribute. These all are the FD. And what is the question is ki, what highest form normalization in the above relation. So what we have said, these all are the alpha, like there are 4 FD. So name, course number, roll number, course number, name and roll number. So all these alpha means of the 4 FD, they must be super key if it is in BCNF. So how you can find? Means they must be key, and we know the formula, we know the trick of how you can find the key. So see here, we will find the closure like name, course number. So name, course number, if we find the closure of name, course number, so we would have name, course number and grade. Similarly, so we would have name, course number, grade, one is missing, and what is roll number. So from name we could determine roll number. So we could write like this one, union of I mean rule. So from this we could determine all 4 attributes. So this one will be super key. Okay. Similarly, from roll number and course number we could determine roll number, course number, grade, and one is name. So name, from roll number we could determine. So ultimately we could determine all attribute. But from name and roll number we cannot determine all the attribute, because from name we could determine only roll number. And there is no way to move on. Okay. So from name we could only determine name, roll number. Similarly, from 4th one, from roll number we could only determine name and roll number. So this 3rd and 4th FD are not key. The left side of 3rd and 4th FD are not key. So this is not BCNF. So what we will see? So this particular FD, we will check if their right hand side is prime attribute, then we could say that this will be the BC 3rd normal form. We have proved that this particular relation is not in BCNF. Why? Because the left hand side of 3rd and 4th FD are not super key, any potential key. Okay. So what we will see? It's right. We will see its right hand side. If its right hand side is part of key, or we can say prime attribute. So what is the right hand side? Roll number and name. If it is prime attribute, then we could say then this relation will be 3NF. So of course we have already proved that name and course number are what? Name and course number are what? Key, super key. So name becomes the prime attribute. So one is proof. Similarly, in the second, roll number and course number are what? Super key. So roll number is also what? Prime attribute. So we have proved that name and roll number are prime attribute. Prime attribute, it is a part of the key. So name, course number, roll number, course number. So roll number is part of this and they are key. So they are part of the key. So they become the prime attribute and right hand side become the prime attribute. Then we can say this particular relation will be in 3NF form. Okay, it is not in BCNF form. If it is not in the highest, then we will check for the next level. I mean 3NF, and of course 3NF will have more repetition than BCNF. So this is how you could prove. So this is all from the normalization. Okay. So we have covered BCNF, 3NF, 2NF and 1NF, and based on the functional dependency theory. That's all. Okay. Thank you everyone.